Now we'll be taking two more cases when the limit does not exist. So if I write the function fx as modulus x divided by x, and I want to find its limit when x tends to 0. So the methodology that I just told you, the left hand limit will be limit x tends to, I'm checking it at 0, so this will be 0 minus fx. So this is limit h tends to 0 f 0 minus h. You remember, I have to replace the function by a minus h, but here my a is 0, so it is f 0 minus h. So this is basically limit h tends to 0 f minus h. Now we put h minus h here. So this is limit h tends to 0 minus h upon minus h. You know, this is h, so this is limit h tends to 0 h upon minus h. So h's cancels and this is minus 1 because h is out of the picture. So this doesn't have any meaning. This is just left with a numerical value, that is minus 1. So the left hand limit is minus 1. Now let's check with the right hand limit. So repetition of the process. Limit x tends to 0 positive fx. Our method tells us this will be limit h tends to 0 f 0 plus h. This is limit h tends to 0 f h. I have to put h here. This is limit h tends to 0 h upon h. So this is h upon h, that is 1. So you found that the left hand limit is minus 1 and the right hand limit is 1. So this is a divergence. We don't reach a particular value. So in this case, the limit does not exist. So this was one case where the limit does not exist. Now one more example when limit does not exist, but we have to check it. I'm taking a function fx equal e to the power 1 upon x minus 1 upon e to the power 1 upon x plus 1. So see this, fx e to the power 1 upon x minus 1, and in the denominator e to the power 1 upon x plus 1. Now I'll check the limit again at 0. So now see carefully, this requires a little bit of logic. Left hand limit is limit, I'm checking the limit at 0 again. Limit x tends to 0 minus f 0 minus h. We have done it 2 times before. Limit x tends to, limit h tends to 0 f 0 minus h. So this is basically limit h tends to 0 f minus h. So I'll put minus h, I'll put minus h at the place of x. So this is limit h tends to 0 e to the power 1 upon minus h minus 1 divided by e to the power minus 1 upon h plus 1. Alright? Now what to do now? This looks a bit tricky, but then it's not a big problem. You need some logic here. Limit h goes to 0. Take the reciprocal. 1 upon e to the power 1 upon h minus 1 upon 1 upon e to the power 1 upon h plus 1. Now, there is some, arguing here. H goes to 0. Now see here. H goes to 0. So h becomes extremely small. 1 upon h becomes extremely large. H becomes extremely small. 1 of h becomes extremely large. So 1 upon extremely large becomes extremely small. I mean, that becomes 0. Again, h goes to 0. 1 upon h blows up, becomes very big. E to the power very big is very big, and 1 upon very big is 0. So this is simply 0 minus 1 upon, by the same logic, 0 plus 1. So this is minus 1. So our left hand limit is minus 1. Now how about the right hand limit? So now the right hand limit. Our definition says that this is limit x tends to 0 plus fx. Our algorithm says that this is limit h tends to 0 f. I have to replace the x in the function by 0 plus h. So this is basically limit h to 0 fh. That is basically limit h tends to 0 e 1 by h minus 1 e 1 by h plus 1. Now again there is a problem. What to do? Now you cannot, as I argued in the last case, now you cannot say that this h can be put here, then this becomes too big, infinity minus 1. I mean, these things don't make sense. So even in applying the logic, there have to be some, structural argument that has to be put before that. So what you need to do, that limit h tends to 0, divide this by the same thing. That is 1 minus 1 upon e to the power 1 upon h, and 1 plus 1 upon e to the power 1 upon h. Now you can apply the logic. Now h is 0, very small. 1 upon 0 is very big. 1 upon 0 is very big. E to the power very big is very big. 1 upon very big is 0. So this can be 1 minus 0 upon, by the same logic, 1 plus 0. So that is how much? That is 1. So you just saw that the left hand limit was minus 1, but the right hand limit comes to be plus 1. So the two limits are different, they are not converging, so this also doesn't have the limit. So we have proved the two cases where there is no limit. So to sum up what we did in today's class, that we first discussed the concept of limit. We did it with the help of the graph, then we did with the help of the epsilon delta argument, and then I gave you some methods, some illustrations how to calculate that. So basically we are trying to, in our talk on the various topics, we'll be trying to balance the conceptual side on one hand and the problem solving strategies on the other. Now the problem most of the times is that either it is too much of concepts or too much of problem solving. but you need to find an intermediate way in between these two, so that you need to balance the concept on one side, you have to be strong in that, and you should also obviously be good at the problem solving. So we'll be trying to address both the aspects. But today's discussion was mainly with the concepts. In the next presentation, we'll be putting up some problems, and we'll be giving you the solutions of that, but that we can do later on. So in the meantime, I'll advise you to go through the concepts once or twice and be at ease with these concepts. Thank you for watching.